Now I'm going to jump ahead historically a little bit to another point of view about functions. This came a bit later than a lot of the other sort of crises and reevaluations of mathematics that were spurred partly by Fourier. But it's a good place to talk about it, and under the guise of what is a function? How do we think about functions? Some big names in the early development of this view of functions, right in the early part of the 20th century: Lebesgue, Riesz, Fisher, and Fréchet, lots of other folks, but those come to mind. And it's a point of view that says that a function is not just sort of an object in isolation. Like, here's a sine wave. You don't want to analyze it just in isolation. You want to analyze it as a member of a family or a space of functions. So here's a kind of a schematic viewpoint of that. We'll say that one of these basic sine waves, one of the building blocks that we use in Fourier analysis, let's say, we're going to just kind of put it, maybe you could even think of it as a sort of a catalog. We're going to put it right here and say that's just a placeholder for this function. And then here's a function that in some ways is rather like that guy. It's got some extra wiggles, but if you look at the difference between these guys everywhere, it's rather small. And so this guy gets put in that catalog or that space of functions in a location that's relatively close. And this is not put in any kind of arbitrary way. It turns out that there's a very precise way. There's many ways, but there's sort of one ideal way for most Fourier applications to determine exactly where these guys should be and exactly how far away they are. Here's a function that's, again, kind of a wiggly function, the kind of thing you'd get out of the Fourier process, but is rather different. It goes up, down, up instead of medium, up, medium, down, medium. And so this is rather different from these two guys. So I'm trying to indicate that it would occupy a location that's relatively far away from these two close neighbors. And so it turns out that every function, or at least every reasonable function, even halfway reasonable, much more general than what Euler would have thought of as a function, can be put in a space of functions that's particularly adapted to the Fourier idea. And that's really cool. So let me talk a little bit about some more details about this version of function space. What this allows us to do is not only sort of catalog them and talk about how functions are close to each other or far away. It really allows us to do a kind of geometry with functions. There's a reason that I put axes on this and made it look like a geometrical space, and why we call it a space. It turns out that notions of distance certainly make sense, and I alluded to that already, that these two functions should be thought of as close and this is further away. It turns out, though, that notions of angle and things like the Pythagorean theorem actually work in this version of function space, putting these functions all together in one abstract framework. It turns out to be hugely powerful to do that, both intuitively and calculationally. It gives you a bird's eye view of all functions all at once. It gives you intuition about, yes, these are close together and this is far away, and that has real consequences about that are not expected. And it gives you incredibly powerful calculational tools. So this is actually a very natural thing. The one reason I'm putting this in right now, this is a very natural thing from the point of view of Fourier, even though it took a while for people to really assimilate this, a while meaning 100 years. So the building block point of view of assembling a function is exactly what Fourier is talking about. He's not talking about a formula that gets you the function. Let's say this is a complicated function we want to describe. He's not saying here's a formula that gives it to us right at once. He's saying build it up by a sum of simpler pieces. So here's an idea of that in function space. You start out with 0. The 0 function, which is just a flat line, the dead guy, okay, always gives the value 0. That's the origin in our function space. Now, we take a pretty big amount. Notice this green segment is pretty big. We take a big amount of a very simple function. Let's say it happens to go off in this direction, okay? And so we're going to add to the origin that much, and so we're going to get to this point in function space. Now, we're going to add a smaller amount of a tighter wiggle. This is, again, this idea of building something that's going to eventually be like a square wave that we were trying to do for the original heat analysis. Okay, so that's going in a different direction. It's a rather different kind of function, and we're adding that in. It's a smaller amount. So we are walking from this baseline of a pretty simple function, walking a medium amount, not hugely far, to a new more complicated function. Now we add in another wiggle of a different type. So that's going to be in a different direction, but it's smaller because these wiggles all get smaller as you add them in. Then we add yet another wiggle in a novel direction, but even smaller. And if we continue this, we're going to have a schematic version that allows us to do precise geometrical calculations with intuition and calculational power that analyzes this function. It's really great. So eventually, what we want to do is we want to think of kind of an infinite path, adding this guy, then this guy, then this guy, this guy, and adding an infinite number of things, getting smaller and smaller to the ideal, we're going to get this flat line up here. And really, it's a square wave. It really goes down, up, down, up. But again, the window that we're doing is just the part that shows the top part of this function. And so we'd like to be able to do that in a precise way that's rigorous and makes sense. But that's a very cool thing. So again, the idea is that we've got this building block point of view of how we create a function like this from simpler pieces. So one of the big things here, though, is this idea, and from the start, this was one of the most controversial things about Fourier. Whether or not you think about it in this abstract and sophisticated way of a function space or not, we're still trying to do an infinite sum to get the precise answer where the wiggles all magically disappear. They're not just small, they're not just too hard to see. In the limit of the infinite sum, we really are supposed to get exactly this very, very simple function made out of wiggles, which is, again, really surprising. Okay, so that gets to one of the big controversial things, and one of the things that really started to remake mathematics. What do infinite sums mean? So this could be a talk in itself, of course, but just a couple of examples. Classic example of an infinite sum, if you take 1 plus a half plus a fourth plus an eighth plus a 16th, you can add up, you can get a notion of what it means to add up this infinite sequence of powers of 1/2, taking 1/2 of the previous term each time. And it actually has a very simple answer. Turns out it's equal to 2. This is related to Zeno's paradox, that if you travel a 1 unit, that's halfway from 0 to 2 on a number line, and then you travel halfway again, that gives you a half, and then you travel halfway again, and halfway again, and halfway again, you can start to convince yourself that it would make sense to say, hey, maybe the addition of all those is going all the way from 0 to 2 on the number line. So I'm not going to spend a lot of time on this. Hopefully you've seen at least a little bit about this idea, that it makes sense to, at least sometimes, to add up an infinite number of things. Now, a great classic example where that doesn't work is, here's another sequence of numbers that are still getting smaller as you go. You're not trying to add like 1 plus 2 plus 3 plus 4, which would be pretty hard to get a finite answer out of. But if you add 1 plus a half plus a third plus a fourth plus a fifth, it turns out that actually the only meaningful answer really is infinity. And the difference here is that these numbers, 1/4, 1/5, etc., are not getting small nearly as fast as 1 over 2 to the n, inverse powers of 2. So there's times when infinite sums make sense and give you a finite answer. There's times when they don't make sense or they give you an infinite answer. Here's an example where you can't even put in any symbol. 1 minus 1 plus 1 minus 1 plus 1 minus 1. Let's try to do that from the start. Well, if I only include this term, it's 1, clearly. But then 1 minus 1 is 0. But then 1 minus 1 plus 1 is back to 1. But then 1 minus 1 plus 1 minus 1 is back to 0, etc. If you try to do it by sort of sneaking up on it, by looking at what's called the partial sums, any bigger and bigger finite sums, finite portions of this thing, it keeps going back and forth between 1 and 0. That doesn't seem to settle down to any kind of meaningful number. Now, Euler would not have thought of it. Euler did claim to make sense of such things because he didn't think of it in this step-by-step process of, hey, let's try to sneak up on it by taking just the first term, just first and second, first, second, and third, first through fourth. He thought, is there some magic formula that we already know the answer to in some way that seems to give this in some case, and then we'll just plug it into the formula. That works sometimes. It does work in certain contexts, but it's really problematic. And even he got flat-out wrong answers with it sometimes. And what happened with the Fourier idea is that it was just incredibly easy to get nonsensical or wrong answers by just trying to do it all at once and not sneak up on it. So the Fourier sums didn't come from the usual sources that Euler's came from, things that really sort of are tied to formulas. One formula that gives the function right off the bat. They're really built out of pieces. So Euler's ideas were not useful for this. It was clear that the meaning of the sums that were the infinite sums coming from Fourier was quite tricky. It was not at all clear when it worked or didn't work. And that was a big problem. If you took Fourier seriously, which people started to do after Lagrange and Poisson, kind of about a generation after that, where people said, God, this is too good to throw away. It was still really not clear when it worked, and that was disturbing. How do you know if your tool is working and you trust your tool? Okay, so related to this issue of infinite sums and whether they work or not is kind of a bigger idea. Just does calculus work as advertised? Calculus had been around for, in some sense, a fairly modern form for well over 100 years. Let's say 150 years at this point, since the days of Newton and Leibniz and many other people who don't get nearly as much credit as they do. We have these incredible tools from calculus, and I'll talk about them in detail in a second. Does it really work as people thought it worked? And in particular, does it work on the new functions that the Fourier process makes available? Things that are super easy to create, and yet calculus doesn't seem to work. And I've talked already about this kind of example. This is a particularly spectacularly bad example from the point of view of calculus. Not only is it maybe a little tricky, or we're not sure if we're going to get the right answer, this is something that is so nasty from the point of view of calculus that it just really horrified people that this was so easy to create using Fourier methods. So let's look very briefly at the two main concepts of calculus. The two main concepts are taking a function. I'm trying to kill my alarm. There we go. Taking a function and look at the graph of the function and look at the area under the graph of a function. That's a tricky thing if this is a curve and not something like a straight line where you can't use ordinary Euclidean geometry. Okay, so is this something that's always okay? People felt they had a pretty good intuitive idea of what was happening here after calculus had been kind of codified in its original form. The other notion, basic notion of calculus, is a notion of a derivative, the slope of a curve, or more precisely, you draw a tangent line to the curve, which means the line, like here, this red line, is the line that best fits or best approximates this curve right at the point where you choose to make it tangent. And that hopefully will have a well-defined slope, and that will give you a notion whether the curve is increasing or decreasing, or how fast things like velocity and acceleration are calculated with derivatives. Is this always okay? Okay, if these are the only kinds of pictures you ever draw, these kinds of nice curves, these kind of Euler-style or Gauss-style functions, you can convince yourself that most of the time this is going to work just fine. Okay, but with Fourier-type functions, it's going to be very much harder. Okay, so integrals, area under a curve, totally easy if it's a straight line. You're going to get, at worst, a trapezoid. Okay, it's harder to make the sense of this, but it's okay, and you can use powerful tools like the fundamental theorem of calculus, things that go back to Newton and Leibniz, if it's this kind of function. Okay, but what about this kind of function? Okay, I'm not as sure that we can really figure out exactly how much area is under this jaggy thing. Precisely, you can get an approximation, but can we ever nail it down precisely? Ooh, that's going to be really tricky. And especially since the main tool that Newton would have used here is the fundamental theorem of calculus that calculates things like areas under a curve by relating them to derivatives. But derivatives are about nicely, smoothly varying curves that have nice tangent lines that are going in a well-defined direction at every point. That's just not true of this function. Remember, what's supposed to be true of this function is if you zoom in at any point, it's fractal. It's still jaggy. It never settles down to having a precise, nice direction, a tangent line. Okay? And this function here, whoa, this is, what's the area under this guy? Does it have any? Does it have a lot? It's really unclear. And so you could say, and a lot of people wanted to say, okay, we'll just make sure we disallow these kinds of functions. They're too nasty. We just say these are not mathematics. These do not deserve to be math, or at least we're not going to try to do calculus with them. But it turns out that when you describe even a nice function in the Fourier style as a sum of wiggles, it was very hard to know how to get the right answer. Even if there is an obvious right answer for the area under it or the slope of the curve, it was really hard to tell how to do that in the Fourier style. So focusing a little more on derivatives, the slope of a curve or the slope of the tangent line. This is something that's usually people understood was a really nice process and seemed to work well. In particular, it satisfied the superposition principle. That if you took two wiggles, two different kinds of functions, and you knew their slopes at a point, and you added those functions together, the slope of the sum of those functions, the combined wiggle, is just the sum of the two slopes. Add two numbers. Really nice. Okay, well, what about infinite sums? What if you take an infinite number of functions together, add them up? So let's suppose it makes sense that we've avoided the known pitfalls about adding up an infinite number of things. Is that still true? Can you figure out the slope of the resulting curve that's an infinite sum? Is it just the sum of the slopes, the numbers for the slopes? Okay. Well, the short answer is it seemed to work okay before Fourier. There was to some extent, people had done this, and it seemed to work before Fourier. But it can't possibly work in every case. And I'm not going to go into the details, but this was basically this was the key to Lagrange's objection, that he could see that this can't possibly really work in some of the simple cases that Fourier seemed to be claiming it worked in. And certainly in this kind of case, whoa. This is actually, again, this is a sum of wiggles. And it's even a fairly well-controlled, nice sum of wiggles, of sine waves that are beautiful functions in terms of calculus and derivatives and slopes, like this. Okay, it's a sum of these guys. And yet it turns out to be something that never, ever has a nice slope. Something is weird here. Okay, so derivatives especially were a huge problem for Fourier analysis, especially since, what is he doing? Why was he interested in superposing these wiggles? He's solving a differential equation. That's an equation specifically about derivatives, about slopes and rates of change. Okay, so that makes it especially weird that it actually works or seems to work. And in fact, it really was working. It wasn't illusory. He's solving a differential equation using a tool that seems to have special problems being consistent with derivatives. What's going on? And when will it work or not work in general? It seems to work in his case, yet Lagrange and many others can easily come up with examples where it seems like it shouldn't work. Very, very confusing. Let me end this part with just talking about an important historical figure and kind of put this in context. I would say that what's going on here is the ghost of Bishop Berkeley is arising in this case, one way to say it. So George Berkeley was one of the best-known opponents of early calculus. The early version of calculus was really anything but rigorous by our modern standards. They focused on notions of infinitesimal quantities, which were finally rigorized in the 1960s. But no one really had anything like what a modern rigorous notion of these infinitesimal quantities in hundreds of years ago when calculus was being founded. And he was the preeminent opponent. Many other people focused on this, that these notions didn't seem to make any sense. Like an infinitesimal quantity is a number that's smaller than any number possible, any ordinary number, and yet not zero. And he just thought that doesn't make any sense. Okay, he really made clear, he gets a bad reputation, and I used to think very ill of him for being kind of anti-mathematical, but he really made clear that Newton and the others were not rigorous in sort of the standards of, say, Greek mathematics. Now, that was not ever a reason to dismiss calculus. And the fact is that nobody abandoned calculus because even though there were sort of philosophical objections and the justifications people had were suspect, there were no obvious contradictions. You could do the calculations, and it always seemed to work until Fourier came along. Here we have a case where you start taking derivatives, and for one method gives you one answer, the other method gives you another answer. And that's really bad. That's not just a philosophical objection. That's not just, oh, you're not explaining it well. It's, I don't know which one is the right answer. I don't know how to tell. Okay, so it really revived. It wasn't the first case when people said, hey, calculus is sketchy. It really revived the slumbering objections that had always been there, but it made it much, much more crucial to resolve those objections. It was not just, oh, the philosophers don't like it, but we mathematicians, engineers, scientists love it. It really made it a central mathematical issue to resolve those contradictions. So in the next section, the next video, I'll talk about the slow path towards actually resolving those objections, and how it really remade all of mathematics, not just Fourier analysis or even all of calculus.